Quiz 6 solutions. We're going to start with chapter 8, section 2, number 2. It says a picture frame measures 12 centimeters by 20 centimeters. 84 square centimeters of a picture shows inside the frame. Find the width of the frame. To me, this seems like there's not enough information in here to even do this problem, because when I hear this, I'm thinking, okay, 12 by 20. So you have like something that's 20 long, 12 high, okay, 20 here and 12 here. And then, okay, you have 84 square centimeters, but it's not specified what that shape is. I mean, is it like something like this? Is it something really long and thin like this? It seems to me that this is not well defined and that this could go a lot of different ways. This is the trick right here. Find the width of the frame. That statement right there implies that it's not different, that the width is the same all the way around, right? Like with that first square that I drew was really thin. The width of the frame would be really thin. Then it would be really thick. Well, by saying find the width of the frame, it implies that the width is the same all the way around. And so the picture we end up with, and again, I hate this. It seems ambiguous to me. If I were writing this problem, I would say the width is the same all the way around. At any rate, what we're doing here is we have a width that's the same all the way around. Okay. And that's what we're supposed to find, is that width. So let's give it a name. Let's call it X. The width from here to here should be X. I'm going to go ahead and label that right here to say that that distance is X. I'm not going to label everything, but I understand that that distance is X. Also, that distance is X. This distance right here from there to there is X. And ditto down here. Again, I'm not going to label all of it, but the distance from there to there. Okay, and so just kind of getting everything nice, looking good here. We're saying the distance from the very top to the bottom is 12, and the distance from the far left to the far right is 20. Okay, and it says that 84 square centimeters is this inner part right there. So I'm going to go ahead and write that in here like that. 84 centimeters squared. Okay, so find the width of the frame. Well, what we're given here, and I'm just going to start with this because right now I'm not 100% sure where to go. I just want to try to get down as much information as I can. I've drawn a decent picture, but we could get a bit more out of it. Like this 84 square centimeters, how did we get that? Well, it's that length right there by that height right there. So I'm going to go ahead and label that too. I'll say that this length, I'm going to call it L from there to there. Here's the height from there to there. We know that L times H is 84 centimeters because that's given to us. So 84 equals L times H. Now I could see if I could relate L or get L in terms of the thing I'm looking for, this width here, which is what I'm calling X. I'm going to say X is the width that I'm looking for, right? If I could get that L in terms of X and get that H in terms of X, then I'll have one equation with one variable, and I should be able to solve. So let's see if we can do that. L, now when I look at L, I'm thinking, so how did we obtain L? Well, you could think about this as taking the length 20 and then chopping off those two ends right there. L is what's left. So in other words, this length right here is X. This length right there is X. And L is what you get when you take 20, you subtract off one X, and you subtract off another X. So L is 20 minus X, or we could say 20 minus 2X right there. Okay, first bit. Play the same game with H. Okay, how did we get H? Well, you took 12 and you subtracted off an X from here. You subtracted off an X from here. And then the thing that was left was that length right there, H. So we could say, okay, H is 12 minus X, or we could simplify that and just call it minus 2X. There we go. Okay, so I have my equation. I can reduce this down into one variable, right? I could say L is that guy, H is that guy, and we should be good to go. So let's do it. Just going to substitute L in there, which is 20 minus 2x. H is 12 minus 2x. Okay, that looks good. So I'm going to go ahead and get rid of a little bit of our work here, just to give me some room for calculations. All right, now what do we need to do? Well, how about first, outer, inner, last with this guy? Because I can see that this is going to turn into a quadratic. And quadratics, I know, at least the easiest way I know how to solve them is to get them equal to 0. That's usually always my first step. So if we FOIL this guy out and get something x squared plus something x plus some constant, I can bring this guy over and hopefully everything will be nice. So let's see what we could do. Okay, so 84 equals first, outer, inner, last. 12 times 20. Let's just see, 20 and 12. Multiply those together. I get a 0 and a 4 and a 0 and a 2. So that's 240. Outer gives me minus 2 times 20 or minus 40x. 12 times minus 2 is minus 24x. Finally, a negative times a negative is a positive. 2 times 2 is 4. X times x is x squared. There we go. Okay, so 84 equals 240 minus, so 40 and 24 are 64 x's, and then plus 4x squared. What I like to do is rewrite this with the leading term over here. So I'm going to go ahead and do that. 4x squared minus 64x plus 240. So I just rearranged those guys right there. I'm going to go ahead and subtract off that 84. So because I know I'm about to get this thing equal to 0. So let's subtract off the 84 minus 84 right here. Oh no. Okay, let's go ahead and make this a 10 by dropping this guy down to a 23. And then 4 and the 10 leave me a 6. Yep. And then 8 and 23, it should be, let's see, 23, 13, or is it 15? 8, 9, 10, 11, 12, 13, and another 10 would be 15. So 1, 5, 6. Does that work? And then, yeah, 156. That should be it. So I'm just going to rewrite all of that as plus 156. Now, if I were so inclined, I could use the quadratic formula. It will probably be easier for me to factor this, and especially since this occurs in the book before they even introduce the quadratic formula, you could probably factor this guy. So, and in general, it usually takes less time to just factor something out if you can. So I'm going to do that and notice, like, yeah, each one of these things is probably divisible by 4. That's definitely divisible by 4. That one may or may not be, but we'll see. So why do we care if it's divisible by 4? Well, because I'm factoring out a 4, in case that wasn't clear. What I'm doing right now is I'm going to factor out that leading term, leaving that right there. Factoring a 4 out of 64 should leave me 16. It should be minus 16x. And I'm just going to double check as I go along and do this. If I threw him back in there, I would have 4x squared. Good. 4 times negative 16 should be negative 64. And now, I can't do that in my head. I'm just going to do the long division. 156 divided by 4. So 4 goes into 15 3 times. 3 times 4 is 12. Subtract that off. And we get what? 3, 6. Does 4 go into 36? It does not. Did I do this right? Let's see. 3, 12, 13, 14, 15. Yeah. 36. No. Yes. Yes, it does. Because 36, watch this. 36 is 6 times 6, which is 2 times 3 times 2 times 3. And so divide that guy by 4. Divide that guy by 4 should kill those. And I have 9. It should be a 9, should give me 36. And I could have done that on my fingers, right? With that nifty little trick with multiplying 9s. You go 1, 2, 3, 4. You have 3 over here. You have 6 over here. Oh, yeah. So 9 times 4 is 36, which is what we wanted. Okay. And so that should work out to 39. Okay, so plus 39 right there. Okay, now, 39. That sounds prime to me, but I think it's divisible by 3. So if I'm going to factor this guy out, which is my next step, right? I'm trying to factor this guy all the way down. Then it should break into 2 nice linear factors. If it does, the x has to be first. And 39. Let's see. 3 times something. I think 3 times 12 is 36. Yeah, because of 33, 36. And then one more would be 13. Let's check that. I think that's right. So 13 times 3 is 9 and 39. Yeah, so let's try 13 and 3. That sounds good. So 3 and 13 right here. First outer, inner, last. When I do my outer, I have 13 with another 3. We can make a negative 16 if we make them both negative. And of course, they have to be the same sign because negative times a negative is the only way to get a positive. So, okay, we're good to go. That is that. We can see that this is only true. The only way for this thing to be true is if x is equal to 3, or if x is equal to 13. And so now we have a dilemma. What do we do? Which one of these could it possibly be? Well, one thing to notice is if x is equal to 13, then this width right here is bigger than that entire side, right? That's what that would say. If x were equal to 13, that means that this whole width would stretch all the way down to here. And that ain't going to happen, right? So we could safely throw this guy away and say the width that we're looking for, x, has to be 3. If we're so inclined, we could go and check all this stuff and say, well, 20 minus 3 from here and minus 3 from there would be the same as 20 minus 6. You would be left over with 14, I think, right there. And 12 minus 3 and minus 3, you would be left with, well, 12 minus 3 is 9, minus another 3 should be 6, I think. Let's see, 6, 7, 8, 9, 10, 11, 12. Yep. And so the height would be 6. The length right here would be 14. And finally, 14 times 6, just checking that my H and my L actually give me 84. So 6 times 4 is 24. 1 times 6 is 6, 7, 8 gives me 84. And so, yes, I feel good about this answer. The width of the frame is 3. Chapter 8, section 2, problem number 4 says the width of a photo is 5 centimeters less than its length. The area is 24 centimeters squared. And we are supposed to find the dimensions. That is, find the width and the length. So we're going to start with a picture. Okay. Something's less than something else, so I could go ahead and draw a rectangle. That'll look good. Okay, so it says that the width of a photo is 5 centimeters less than its length. So I guess I'm going to call this here the length. This will be L, and this will be the width. This will be the other one. And we know that the length times the width is the area, right? The area is just the length times the width. And we know that that area is actually 24 centimeters squared. Okay, so we could even start there. We'll say 24 is L times W. But we need to somehow relate these guys together. And it says that the width is 5 centimeters less than the length. So in other words, if we took the length and subtracted off 5, we would end up with the width. There we go. We could go ahead and do that. We could say we'll replace W with L minus 5 right there. And now we'll have one equation in one variable, L, and we should be able to solve that. So let's just see what happens when we do that. And so to be clear, what I'm doing here is I'm saying that W is equal to L minus 5. Okay, and so 24 equals L times W is L minus 5. So I'm just going to replace it, L minus 5, just like that. That gives me, so I'm going to hop over, distribute that L, and I get L squared minus 5L equals 24. But how about I bring that 24 over? Right, I'm going to go minus 24. Why am I doing that? Well, because I know this is a quadratic, right? This is a quadratic equation. And it's way easier in general to solve these things if they're equal to 0. So that's just what I'm going to do. Hopefully this thing can factor. And that's what I'm going to try to do. See if it does. 0. If it does, it should break into L here and L here. Now I'm just thinking, okay, what times what is 24? We can do this a lot of different ways. How about 4 and 6? If we tried a 4 and a 6, but there's no way to add or subtract a 4 and a 6 to give me 5. So let's bring it, how about 2 and 12? 2 and 12 is not going to work because that's not going to give me 5. Did I do this right? Let's see. 24, let's just see. Okay, so 24 is 2 times 12, which is 2 times 6, which is 2 times 3. And so what if we did that? 2 times 2 times 2, or 8 times 3. So 8 and 3, oh yeah, 8 and 3 can give me a 5. So let's do that. 3 and an 8. And it's obviously apparent that I just don't know my times tables, otherwise I would have been able to remember that guy. But anyway, okay, so it needs to be a minus. So that means the last term needs to be minus, which means these have to have opposite signs. So minus takes over here, so the 8 has to have the minus. That guy has to have the plus. Let's double check that. First, outer, inner, last. First gives me L squared. Yep. Outer is minus 8L. Inner is plus 3L. Minus 8 plus 3 is a minus 5. There we go. We're good. Then the minus and the plus give me a minus 24. Great. Nice. So I could solve this and say, well, this is 0 because we're saying 0 is equal to something times something. The only way for that to be true is if that's equal to 0, in which case L would have to equal -3, or L is equal to 8. L is equal to +8, then that whole thing is 0, which makes that entire equation equal to 0. And if you want, you could plug that back into the very beginning and you get everything you're looking for. So, okay, one of these doesn't make sense. And it's pretty clear to me that L cannot be a negative number the way we set this up. You might get in the habit of thinking, oh, length can never be negative, and just throw it out altogether. Well, it might be. In the context of this problem, it's not. But if we had set something up, say, on like an XY axis, or maybe a north-south versus east-west, and you end up with an answer like -3, that might actually make sense in your problem if -3 means you've gone 3 meters west or something like that. So, but in the context of this problem, we don't have any coordinates or anything like that. All we're working with is lengths. And in this case, these are all positive lengths because we haven't even introduced an axis, Cartesian coordinates or anything. And so in this case, yes, L equals 8 would be the length that I'm looking for. So I would say L is equal to 8 right here. I'm trying to find the dimensions. Then L or W would have to be L minus 5, which is 8 minus 5, which should be 3. And I could double check that 8 times 3 is indeed 24, which I had no idea of earlier. But yeah, there we go. That looks good. Now you might have set this up differently. You might have said way back here. So let's keep this up on the board. L equals 8. That is what we got from all this work here. You might have been setting all this up and you said, okay, A is equal to L times W. And it says that oh, it was 5 centimeters less than its length. Well, then that means that W plus 5 is equal to L. What if you had done that, right? Because it's true. If you take, if the length is, if the width is 5 centimeters less than its length, then if you took the width and then added 5 to it, right, you should end up with the length. And if you had done that, then you would have gone along and said, okay, I could substitute instead of L here, instead of substituting for W, I could substitute for L and say that the area, which we know is 24, is equal to L times W. L is equal to W plus 5 times W, which gives you W squared plus 5W. You have your 24 right here, which you would subtract and say W squared plus 5W minus 4. Then you would factor this guy and say, okay, W and 24, how about 3 and 8, which I would never have guessed. But now you'd say, well, okay, again, they have to, one has to be positive, one has to be negative because of that. It has to be positive. So the bigger one needs the positive here. Minus, then we check it first, outer, inner, last, first, outer, inner. Yep, it comes out to that. Last comes out to that. So we're good to go, which means that W is either equal to 3 or W is equal to -8. You say, wait a minute, no, in our context, there's no negative width. And so that guy's out. And so the width would have to be 3. And you'd say, aha, width is 3. And then you'd say, well, what about the length? Well, it's 5 more than that. So we would have 3 plus 5 is equal to L, which is equal to 8. And you would end up with the same thing. So if you set it up differently, you should end up at the same place if you could remember that 3 times 8 is indeed 24. Chapter 8, section 2, problem number 6 says the hypotenuse of a right triangle is 25 kilometers long. The length of one leg is 17 kilometers less than the other. Find the length of the legs. Okay, so we have a right triangle. Let's draw a right triangle. And what I'm going to do is make one of the legs longer than the other leg. There's my hypotenuse right there. I'm going to show there's a right triangle like that. Now, 25 is the hypotenuse. So that's this guy right here. And in general, what we have is that the legs, let's just call them A and B. If you, by the Pythagorean theorem, if you take the squared, the lengths of the legs squared, add them together, you get the hypotenuse squared. Okay, so that's what we're starting with. Problem is we have 2 variables and only 1 equation. So if I could somehow reduce this down to 1 variable, I'll have 1 variable, 1 equation. I should be able to solve it. So it says that the length of one leg is 17 kilometers less than the other. The way I've drawn this right now is that B is the longer one. So we could say if you take B and subtract off 17, you should get A. In other words, A is equal to B minus 17. That's what I'm going to do. I'm going to take that guy and substitute him in here for A, and then we'll have something just purely in terms of B. Now, we said this in the last problem. I could have done this the other way around. I could have said, well, hold up. If you take A and add 17 to it, you should get B right there. And you'll notice that these are the exact same equation, right? Add 17 to both sides here, and you'll have A plus 17 equals B. A plus 17 equals B. Subtract 17 from both sides of this equation, and you end up with this equation right here. We saw before that if I would have made, what we saw in the last one, that when I made the other substitution into the original equation, we end up with the same answers. And so it doesn't matter which way you want to go to do this. I already chose that I would be substituting for A to get everything in terms of B. So let's go ahead and do that. I'm going to say that A is B minus 17. So that's what I'm doing right here. Now, okay. I know this is going to be quadratic. It's going to be quadratic in B, meaning we're going to have something times b squared plus something times b plus something. And if I get that all equal to 0, that's going to make my life a lot easier. So let's go ahead and do that. I'll start by multiplying that guy out. In other words, what I'm going to do is take this, square that guy, b minus 17. I got to go first, outer, inner, last. First gives me b squared. Outer gives me minus 17. Inner gives me minus 17 for a total of minus 34b. Last gives me 17 times 17, negative 17 times negative 17. And what is that? Let's see. 7 and 7 is 49. Oops, 49. 7 times 1 is 7. 4, 7, 8, 9, 10, 11. That makes it 11. And then we have a 7 times 1 is 7. 1 times 1 is 1. And we should have 289. 17 times 17 is 289. Negative and negative make a positive. So we have plus 289. Finally, plus b squared equals 25 squared. Okay, let's collect like terms. So we'll get this out of the way. We have 2b squareds. We only have 34 or minus 34b. Now, 289 and 25. It'll be nice to go ahead and square this guy out. So let's do that. 25 times 25 is, let's see, 5 and a 2, and there's a 10 to 12. 5 is 1, and 4 and 5. That comes out to 625. So this is plus 289 equals 625. All I did was I squared that guy out. And then I really just moved that guy over there to get all my b squareds together. Now, okay, I'm going to subtract him over here. It might actually be easier for me to just compute 625 minus 289. Okay, so we're going to have to borrow one of these guys. And let's see, it gives me 15. 9 up to 15 is 6. And now, 28 up to 61. 28 would be 38, 48, 58, 68. Or I'm sorry, 28, 38, 48, 58 would be 30. And then another 60, 61, another 3. So how about 33? Is that right? 33? Left over, let's check it. 336 plus 289 should be 625. 336, 289, add those together. 9 and 6 is a 5, carry the 1. That is an 8 and a 4 should be 12. That is a 5 and a 6, 625. Okay, yeah, 336 then. But that would be if I brought it over here, that would be plus 336. So we'll bring it back over and go minus 336. And so minus 336. That's what I just did. I took that guy over, subtracted off. Okay. Okay, there we go. One thing that's nice is I can see all of these are even, and so I will be able to pull out a 2. Let's go ahead and do that. And so that leaves me with a b squared. Half of 34 is 17. 336. Ooh, half of 336. So let's just do it the old-fashioned way. 336 divided by 2. 2 goes into 3 one time, giving me 2 with 1 left over, drop the 3. 2 goes into 13 6 times, giving me 12. 1 and 6 right there. 2 goes into 16 8 times, so that should be 168. It should be 8 minus 168. Let's just make sure we haven't messed anything up. The 2 comes in to give me 2b squared. The 2 comes in to give me negative 34. Yep, 34b. 2 goes in here to give me a negative 2 and 8, 16. Carry the 1. Yeah, sure. Yeah, it works. That'll work. Okay, so now hopefully this will factor out. We could have just right here, as soon as we got to here, just plugged it in the quadratic formula. Problem I could already notice, we'll have to square 34. Yikes, right? That's just going to get really ugly. We'll have minus 4ac and a root. C is huge. I'd rather not. And I'm thinking it'll probably take us less time to do this if I don't screw it up. So we'll see. Hopefully this factors. If it does, it will look like this. It'll have a B right here and a B right there. Right? So now I just need to figure out, okay, what times what is 168? That gives me minus 17 when I add or subtract them from each other. So let's factor out 168. These are pretty big numbers. 168 is equal to 2 times. Half of that would be a 4 and a 3 and a 50. So 50 and 34 is 50 and 34. 84. Something like that. Let's see, 2 times 84 is 168. Yeah, yep, that works. So 84 is 2 times, it should be 42. See anything that's going to work yet? No, probably not. So let's do another 2. Maybe that'll work. 42 is 2 times 21, I think. And 21 is 3 times 7. So here's the factored form of 168 right there. 168 should be 2 times 2 times 2 times 3 times 7. So let's see how we could get this to give me 168 and a 17. 17. What about 21 minus 8? Does that work? I don't think so. 21 and 8? No. 3 and 14 and something maybe, because we have a 2 and a 7, and then a 4 times a 3 would be 12, right? 4 times 3 is 12, and then a 2 and a 7 is 14. Yeah, that's not going to work. That's not going to give you 17. Another thing to note is that one has to be positive and one has to be negative, which means the negative one is going to have to be bigger. So I'm already not in, it's going to have to be 17 units bigger, and we are not anywhere close to that. So I'm probably looking a bit too much, actually. Let's try. What is 7 times 8 and 3? No, that's way too big. So how about 4 and 3? So we could do 6 times something, maybe. 6 times what? Well, if that's the 6, the 2 times 3, then what's left over is 4 and 7. And 4 times 7 is 28, I think. Wait, 4 times 7, is it 28? Because 4 times 6 is 24. So another 4 would be 28. So 6 and 28. Can I subtract that off to get 17? No. Because yeah, that would be 22. Man, this is turning out to be a real pain. Usually I see it before this long, but it's probably staring me right in the face. Let's see. I have a 2. 4 is not going to work. So what about try that? Ooh, 24 and 7. Does that work? Let's see. So 2 times 2 times 2 times 3 is 8 times 3, which I believe is 24. So 24 times 7 And then 17, 18, 19, 20, 21, 22, 23, 24. Ah, we got it. Okay, so 24 times 7 should be 168. Since I spent so much time, I want to double check this to make sure I haven't messed this up. Oh, you can't even read that because of that glare. I just wrote 24 times 7 right there. What I'm going to check right now is that 24 times 7 does give me 168. So 4 and 7 is, I just said this, 8 and a 2. 2 times 7 is 14, 15, 16, 168. Okay, you can barely see that. But anyway, so 24 and 7 should do it. So 24 here and a 7 right here. Now, the bigger number has to have a negative. So boom, the smaller number has to have a positive right there. B plus 7 and B minus 24. First, outer, inner, last. First gives me B squared. Outer is minus 24. The inner is plus 7. And we could see that 24 and 7 minus 17, 18, 19, 1, 2, 3, 24. Yes, okay, so that works. 7 minus 24 is minus 17. Now, negative and a positive come out to a negative, and we just check that 24 times 7 is that. Okay, finally, man, that was a pain. But you notice I didn't cut and just come back with the answer. I like to show you what goes on, like in my head, whether that helps or not. So how to troubleshoot, right? Sometimes you run into stuff and yeah. Anyway, okay, so the only way to make this thing equal to 0 is if this thing is equal to 0 or that thing is equal to 0. If that thing's equal to 0, it means that B has to be negative 7. That thing's equal to 0, it means that B has to be positive 24. And in the context of our problem, right, we're not on a coordinate system here or anything like that. We have to take our length to be positive in this situation. And so B is equal to 24. And then A is 17 less than that, right? So B minus 17 is equal to A, but that's 24 minus 17 equals A. And I think we just saw that that was 7. It should be 7. So 24 minus 17 should be 7 equals A right there. And so A equals 7. Find the length of the legs. We just did. There's your answer. Chapter 8, section 2. Number 8 says find 3 consecutive integers such that the square of the first plus the product of the other 2 is 46. So with consecutive integer problems, we have to remember one nifty property about the integers is that if you have an integer, call it n, the very next one can be written as n plus 1. And the very next one after that can be written as n plus 2. Any integers like this, right? Like -3, add 1, you have -2. Add 1 more, you have -1. Those are consecutive integers. Or 4 plus 1 is 5. 4 plus 2 is 6. And so those are, so that's the way we want to write this. Another thing we notice right off the bat is it's going to give us a bunch of things to do with these consecutive integers. And we're going to try to put this all in an equation. And if we could have one variable, then we can figure this out. We could do, which is not going to help us, but we could say, well, okay, 3 consecutive integers. Okay, an integer, how about n, m, and l? Okay. We'll call those our 3 consecutive integers. And it says the square of the first, okay, n squared, plus the product of the other 2, plus m times l. So the square of the first plus the product of the other 2 is equal to 46. You go, okay, there's my equation. Yeah, but that equation has 3 unknowns in it, right? So the whole idea is, like, yes, this is what we're going to do exactly, but we're just going to relate them all together by saying, well, hold up, m It's the next one. So we could write that as n plus 1. And that is the one right after that. So we could write L as n plus 2. So let's go ahead and do that, right? So these are my 3 consecutive integers. I'm just going to rewrite this. In fact, I'm going to say, okay, the square of the first, which is n squared, plus the product of the other two, so n times L here, or n plus 1 is n plus 2, says that sum is equal to 46. All right, and what do we have? Well, this is a quadratic, right? And because I could tell that the highest order here is going to be n squared, we're going to pick up another n squared right here. But I know that if I could turn this into an equation equal to 0, I should be able to solve this thing. So let's go ahead and multiply this out. This is n squared plus first, outer, and last. N squared. Outer is 2n. Inner is 1n for a total of 3n. 1 times 2 is 2 equals 46. So let's consolidate here. We have 2n squareds. Yeah, 2n squared plus 3n plus 2 equals 46. Or how about I go ahead and bring that over? So that'll be plus 2 minus 46 on that side equal to 0. Plus 2 minus 46 should be minus 44. Right, so all I did is I just took that 46 and subtracted him over here. Minus 46 plus 2 minus 44. Okay, that looks good. Now, okay. I could see that I'm not going to be able to factor out a 2 because then I'll end up with 3 halves. Uh-oh, that's ugly. Maybe we could factor this guy out. We could, of course, just jump right into the quadratic formula, but this might actually be easier to not do that. So let's just check and see if this thing does factor into linear factors. One of them is going to be a 2n and one of them is going to be an n here. Right? That's the only way for my first multiplication to give me a 2n squared, unless I want to get really tricky, which I don't. Right? That's the whole point of doing this. Okay. Now, 44. What's 44? Well, 44 is 2 times 22, which is 2 times 11. So there's not much to work with here. That's 4 times 11 or 2. So let's see. It's either going to be 2 and 22, or it's going to be 4 and 11. That's actually, so yeah, my intuition to go ahead and try factoring, this feels good. Unlike the last problem we did where, boy, that was rough, and it probably would have been faster to just do the quadratic formula. But anyway, so I'm thinking my intuition's telling me 4 and 11 here. I could be wrong. Well, let's just try it. Where will we want the 4 and where will we want the 11? I'm thinking we'll put the 4 over here. And let's just try the 4 here and the 11 here. Why? Well, the outer gives me 8. The inner gives me 11. 8, 9, 10, 11. The difference is 3. So that looks good. Now the question is, well, I have a minus here, which means one of these has to be plus, one has to be minus. And so we're going to want the bigger one to be plus so that we have more positive left over. And I could see between 8 and 11, 11's the bigger one. So I'm going to say plus that guy, minus that guy. Okay, so now what does that give us? Let's double check that and make sure that that does give us what we want. First, outer, inner, last. That gives me 2n squared. Good. Outer is minus 8n, inner is plus 11, and 8, 9, 10, 11, that is 3n. Okay, so I'll get there. The last is 4 times 11, which is 44, and it is negative, and so we're good to go. So that gives me 2 possibilities. For this to be 0, either the first thing is 0, and if 2n plus 11 is equal to 0, then n has to be minus 11 over 2. Right, I brought the 11 over to this side, divided by 2, okay? In the other case, n would have to be 4. Now, thing is, These are consecutive integers. Negative 11 halves is not an integer, okay? It is a rational number. You cannot reduce that guy. Now, if you had negative 12 halves, if it worked out that way, and then you would have, oh, minus 6, that's an integer. You say, oh, but it's negative. Doesn't matter. Integers can be negative. And so your original numbers would be minus 6, minus 5, and minus 4. And that would be fine. Doesn't happen to work this way, though, right? It's not 12, it's not negative 12 over 2. So it doesn't reduce down to an integer. And so this possibility is right out. We have to have integers. So that is not good. So our only remaining answer is n equals 4. And so it says to find, and this is not our answer. Do not answer n equals 4, because that's not what it asked for. It said find 3 consecutive integers. That's one integer. So let's get all of them out, right? N is 4, so then the next one would be 5 and 6. So what we're looking for, the 3 consecutive integers would be 4, 5, and 6. And let's just double check that when I square the first and add it to the product of the second, that would be 16 plus 5 times 6 is 30. And we do get indeed 46. Yes. Okay. So we are good to go. That works. Just want to stress one thing here. If, let's say, and this is not the case for this problem, but if in the end we got 2 answers, and let's say that they worked out to be n equals 4, which would give you that set of answers, that would be perfectly good. If you had another one that said it, let's say n is negative 6. And you say, oh, screw that, that's out. Well, not necessarily, because negative 6, negative 5, and negative 4, just, it doesn't work in this problem, but it might work in the problem that you're working on. There's another one in this section. I think it's in this section, it might be another section that's like that, where there are actually 3 sets of answers, where you have things like this, where you have 4, 5, 6 work, and negative 4, negative 5, and negative 6 work. And I think it was one more like negative 1, 0, and 1 work. And so if they say just find 3 consecutive integers, then you'd be fine with this. But if they say find all sets of integers, and you ended up with something like this, then you would not be done. You'd have to say, well, here's the first set of integers that work, the first 3 consecutive integers that work. And another consecutive integers that work would be, in this case, minus 6, minus 5, minus 4. Of course, that's not the case here. Just thought it would be a good opportunity to bring that up. Chapter 8, section 2, problem number 10. Airplane A travels 2,800 kilometers at a given speed. Airplane B travels 2,000 kilometers at a speed that is 50 kilometers per hour faster than A, but it does it in 3 hours less time. Find the speeds of each. Okay, so find the speeds of each. I'm going to go ahead and identify that and define some variables right now, because there's a lot going on in this problem, right? I'm already saying distance, time, and rate, right? And so I know that there's going to be a lot going on. I don't want to lose myself in this work, so I'm going to keep my objective in play. I'm going to say find speeds of each. So what I'm looking for is the speeds of each plane. So let's do this. Let's let S be the speed of A. Okay, so S is equal to speed of A. Okay, now I could say let T be the speed of B, but we already have a way to relate it, right? It says that B travels 2,000 kilometers, blah, 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 at a speed. So the speed of B is 50 kilometers per hour faster than A. So another thing I'm going to do up here is say S is the speed of A in kilometers per hour. So S is kilometers per hour. This may or may not come into play, but sometimes it's nice to have that on your page somewhere. So, okay, then the speed of B must be, well, whatever S is plus 50, right? So like if this were going at 100 kilometers per hour, then B would be 50 more, would be 150. It would be whatever S is plus 50. That's going to be the speed of plane B in kilometers per hour. Okay. All right, there's that right there. Now, it says that we travel a certain distance in a certain time and at a certain speed. So I'm going to go ahead and also write down my distance rate, how we could relate distance, rate, and time together. Okay, so we can think of rate, or in other words, speed, is distance over time. Multiplying both sides by t, we get time times rate is equal to distance. I could also divide both sides by r to give me that time is equal to d over r. So a bunch of different ways of writing that. I'm not sure which one I want to use yet, but it's nice to have them on my page. So when I'm struggling, I could go, wait a minute, hold up. Do I have this information? Can I plug this in somewhere? So, okay, we're going to relate this stuff together. Well, one thing we know is that in both cases, we're given a distance. And we have our rates, right? We've already defined them. So we're going to need to make one of these variables drop out somehow, right? And what I'm thinking is if we could relate the times together, I may or may not be right here, but if I could say that the time it takes for one of them to do something. So let's actually get that out as well. It says that it travels in 3 less time. So let's again, since I've said that S was the speed for A, let's say that T is equal to the time in hours, because we're doing kilometers per hour. So the time it takes A to make the flight, right? So to travel the 200 and whatever. So then if B, the time that it takes B, to go its distance of 2000, if it's 3 hours less, right? So then, oh, I didn't do this, right? In hours. This is in hours, right? Then, well, 3 hours less than the time it takes A, it should be T minus 3. So if it took, say, 7 hours for A to fly that much, 3 hours less than that would be, well, 7, 6, 5, 4, 4 hours. And how would I get that? Well, you just take the time, T, subtract off 3. So that's what I'm going to do. Minus 3. So this is the time it takes A, and I didn't write it down to complete the journey, the given journey of the given distance and all that, but that's going to be nice. Okay. All right. So here we go. Almost there. So the distances aren't the same, right? If they were the same, I could just, use this distance formula and set up time and rate on one side, time and rate on the other side. That's not going to work. What I'm thinking, my intuition's telling me to go with this guy right here. Because again, like we're supposed to find speed. In other words, rate is the thing we want. We don't want to get rid of it. We don't want to say, well, distance and time for this one, right? What would we have? We'd say, well, we could relate these, that the distance and the time, and then rate would disappear if we did that, right? We could say the distance for A and the time for A, and then we do something with the rate, we do some magic to see, okay, and we relate the distance of B and the time of B, and then we have distance of B is equal to the distance of A and the time of A and all this. And then, well, where would our rate be? We're supposed to be finding the speeds. Those are the rates, right? And so if you make the rate drop out, well, that's not good. So we're going to make one variable drop out here. And since distances are different and they're actually given, they're concrete numbers, there's only two things we don't know. We don't know time and we don't know speed. Speed is the thing we want to find, right? So the rate is the thing we want to find. It's something we want to show up. So we're not going to make it drop out. So my intuition is telling me this is the way to go. we could relate the times together somehow, right? And then we'll have the given distance, which are just straight up numbers, which is good. You want like a straight up number. And then the rate, which is our variable, will show up in our final equation. Unlike in this one where the rate doesn't show up at all, and then what? So okay, that's my plan here. So I'm going to say, all right, since time equals distance over rate, well, let's just take this and apply it to situation A, right? The time it takes A is t, so t is the time it takes to go its distance, which is 2,800 kilometers, divided by s, right? Its rate, which is its speed, which we're just calling s. There you go. There's its speed in kilometers per hour. Why did I write these units in there? Because I could check myself now, right? I could say, well, wait a second. T is supposed to be in hours. And so what did we just do? We took kilometers and we divided it by kilometers per hour. So you had kilometers in the numerator. You divide it by a fraction, which means multiply by the reciprocal, which is hours. Kilometers. Those guys cancel out. And now we're left with hours, which is indeed what we should have. We're saying this should be t hours. And yeah, you take a distance and divide it by a speed, and what you have is hours. So I feel good about this. I'm just kind of double checking everything. And since I've done that, I'm going to go ahead and get rid of this stuff right here. And that was just to help me make sure I'm setting everything up right. Okay. Now, what about scenario 2? Well, same thing, time. The time that it takes is the distance that it flew and the speed at which it did it. So, okay, just translating that in, the time it took was t minus 3. That equals to the distance that it went, which is 2,000 kilometers, divided by, looks like s plus 50. There we go, s plus 50 kilometers per hour. And we already did the work, right? Kilometers divided by kilometers per hour works out to hours, and t minus 3 is in hours. Okay, so I feel good about that. We want to make the t drop out. In other words, if we could get both of these things equal to the same thing, then we could get rid of that variable. And right now I'm seeing a pretty easy way to do that, right? This guy says t equals this. This says t minus 3 is equal to something. Well, let's just get rid of this minus 3, right? We do that by adding 3 to both sides. That gives me t equals 2,000 over s plus 50, finally plus 3, just like that. Now, remember, this is the same time, right? So it said, yeah, in less time, the time that we're referring to was the same time. Maybe it's 4 hours, maybe it's 7 hours, whatever, right? But it is the same time. So we could say, okay, since that is the same time, if t equals that and t equals that, then that thing equals that thing. Now we have an equation that has the variable that we want in it, so we should be able to solve for it. So for right now, I'm going to go ahead and get rid of this stuff. I would actually not want to do that, but I want to save some space on the board, because as I do these, I would like to go back when I finally get s equals something. I would like to look back and go, oh, yep, that's what I was looking for. This is the speed of this, but we're not going to do that now. Save some space. So, all right. So t equals t. I'm even going to write that. T is equal to t. Yes, yes, it is, Justin. And on one hand, t is equal to this. Okay, so 2,800 over s. That's t, yep, so that still equals t. But on the other hand, t is also equal to this. So I could replace that with that right there. 2,000 over s plus 50 plus 3. Now let's just double check. I have one equation with one variable in it, and that variable is the thing that I want, right? S was for A, and S plus 50 was the speed of B. That was why I erased over there. Okay, so what do we do? Well, I have denominators. Let's kill the denominators, right? So, because that's the only thing that's messing up my life right now, and those denominators. So if I multiply both sides by both denominators, that will kill everything. So I will need to multiply by an S and by an S plus 50. Do that on both sides, S and an S plus 50. Okay. S is over here, cancel, and I'm left with, I'm going to write the number first, 2,800 times S plus 50 equals, okay, the S plus 50 jumps over, cancels with that guy. All that's left is an S, and so 2,000 S. Now, that whole thing jumps over and hits there, and we have 3 times S times S plus 50. Okay, and I can see this is going to be a quadratic, right? That's going to give me a squared term. And so I know the best way of doing quadratics is to get the equation equal to 0. Hopefully we could factor. So let's do that. First, I got to multiply everything out. So 2,800 times S. 2,800 times 50 gives me a big row of 0, 0, 0. 5 times 8 is 40. Right? Yes. 5 times 2 is 10 plus 4 is 14. Ugh, that is 140,000, I believe. So I do that right. Yep, that looks right. So 100 plus 140,000 equals 2,000 S plus 3S squared, right? Because the S jumped in to hit that S to give me a 3S squared. 3S jumps in. 50 times 3 is 150, I believe. Yes. So plus 150S. I want to make sure I did this right because this could really mess up my life in a second. So let's do that. 2,850. We'll do this one more time. We get 1, 2, 3, 4 zeros. 1, 2 zeros. 8 is 40. 2 times 5 is 10 and 14. So 1, 4 right there. Is that right? Yes, that's right. 3 zeros and a 140. Okay, that looks good. It's going to be big, but we'll see what happens. So, all right, let's get everything on one side. The 3s is already, the S squared term, sorry, is already positive. So we're going to keep it on the right-hand side. I'm just going to move this over to look like this. This guy stays over here as 3s squared. Now, we have 2,000s minus 2,800s gives me a minus 800s. Then we plus a 150s, and that should be 650 minus 650s, I believe. Let's just double check that 650 and 150 come out to 0 and a 0 and a 1. 800, yeah, okay. So minus 650s, minus 650s. And finally, the last thing is to bring this guy home, right? Minus 140, 0, 0, 0. Okay, yikes, that's really ugly. And what I'm going to do, I'm actually going to use a calculator for this because yikes, right? Hopefully this will factor. I'm going to go 0 equals, well, like this. This should factor out into, and if it does, it's going to be a 3s here and just a regular s there. Now, 140,000. You know, it might be easier, and we might just do it that way to do the quadratic formula. Unless I seeing anything right off the bat? No, I'm not. So, yeah, why not? It'll be nice. Yeah, why not? Let's just do the quadratic formula. It'd be nice to do it once at least. All right, so. This is B. B is equal to negative 650. C is equal to negative 140,000. A is equal to positive 3. So that means that S is equal to, right? Because it's not X, right? In this case, S is the variable, and so S will be equal to negative B over 2A. So negative B is a positive 650 over 2 times A is 6. Yep. Plus or minus. It's going to get ugly, but I feel better doing this than I do trying to factor that. So let's go ahead and do over the 2A part. 2 times A is 6 again, right? For 2A. 2 times, yeah. Okay, now B squared. I'm going to go ahead and just write it down here. Minus 4AC. So that's what we're trying to find. B squared minus 4 times A times C. Let's see what that is. B squared is 650 and 650. 0, 0, 0, 5 and 5 is 25. 6 and 5 is 30. Yep, and 2 makes 32. Finally, we get a 0. 6 times 5 is 30. 6 times 6 is 36. 37, 38, 39. Oh, this is going to be really ugly. 0, 0, 5, 2, 9, 10, 11, 12. Ooh. 422, 500. All right, that first part. 650 over 6. We'll just leave it like that. 650 over 6. Over 6. Okay, 4 times A times C. 4 times A is 12. Yeah, 4 times A is 4 times 3. 4 times 3 is 12. 12 times C. 1, 4, 0, 0, 0, 0 times 12. Right now, right? I'm working out 4 times A times C. 4 times A was 4 times 3 is 12. Times C is times that bad joker right there. Okay. So 0, 0, 0. Wait, 0, 0, 0, 0. 2 times 4 is 8. 2 times 1 is 2. And just 2, 3, 4, 4. The 1 all together is 0, 0, 0, 0, 8, 4, 5, 6, and a 1. Okay. Minus that, but C is negative, right? So it's a minus times this. So 4 is positive, A is positive, C is negative. So that's a minus. So it should be plus all of that amount right there. 1, 6, 8, 0, 0, 0, 0. This is where I'm going to use a calculator. I'm going to determine what that square root is right there. So the square root of 422,500, 422,500 plus 1,680, 1,680, 000. Comes out to 1450. Okay, so all that right there, I plug that in. The square root of that big number plus that big number is, sorry, let me get this right out here, plus or minus over 6. That thing right there was 1450. See, 1450. Yeah. There we go. Okay. Now, let's see. We could do, well, there's one thing to notice here, right? Given the problem that we're working on, we expect a positive speed, right? Because it's not to say that speed can't be negative if you are talking about, say, an oriented graph where, say, the upward direction represented north. Then negative speed would mean, well, you're going south. In this scenario, we have not oriented anything. We're talking about actual distances, positive times, and so we have to have a positive speed, right? So I could go ahead and throw one of these out. I could see that 650 over 6 minus 1450 over 6 is going to be a negative number because, well, 1450 is bigger than 650. So we could just go ahead and throw that out. We know that in this case, speed can't be negative. And so we're going to have to take the positive answer, which is going to be 650 over 6 plus 1450 over 6. So let's see what that is. 1450 plus 650 is 2100 over 6. It's 350. So our speed of plane A, right? And this is why I would have wanted this to be up on the board, because I get down to this point after all of this crazy stuff that I've done and I go, wait, what? Oh, I was trying to find S. And so I just put a box around S. And that's not what they asked, right? So what was this? Oh, yeah, that's right. S was the speed of A in kilometers per hour, right? And we knew that the speed of B was S plus 50. 50 plus that would just be 400. So finally, our final answer that we're looking for is speed of A is equal to 350 kilometers per hour. And the speed of plane B is equal to 400 kilometers per hour. Chapter 9, section 6, problem number 12. A rancher is fencing a rectangular area with a fixed perimeter of 76 meters. What dimensions maximize the area? Find the max area. Okay, so first thing, let's draw a picture, right? We're fencing a rectangular area. So let's just draw a rectangular. Let's draw a rectangle, okay? Well, let's label the sides too, right? We'll say that this length is X, this length is Y. It turns out, yeah, that's what we want to know, right? What dimensions we want to find X and we want to find Y. So those are the two variables I'm going to be looking for. Okay, I've drawn a picture. Now let's identify the the quantity we want to optimize. Now we want to, it says to maximize the area. So given the picture, let's go ahead and write out a function which gives me that area. The area of a rectangle is the base times the height. So in this case, it's just X times Y. Okay, that is a function, right? It's an input-output relation. The input is the base and the height, right? Two inputs, an X and a Y. The output is the area, okay? Now, let's identify a constraint, because the idea is we don't know how to deal with two variable functions. So we need to find a constraint in order to drop this 2-variable function down to a function of 1 variable. And what I notice is, oh, we have a fixed perimeter of 76 meters. That means that if I started walking here and laying down fence, I would run out. I want to run out by the time I get back to there. That's 76 meters. And so I'm thinking, well, there's a formula for perimeter, right? 2x plus 2y equals perimeter. But let's think this through and just make sure that that works. I like to imagine I'm starting here and walking. I would say, okay, I've walked y and I've walked x. I've walked another y, so I've walked 1x and 2 y's. I walk one more x. Yeah, I would walk a total of 2 x's and 2 y's. Okay, so my perimeter, all right, is just 2 x's, whatever that length is, plus 2 y's. Okay, and that's going to give me my constraint because we're constrained to the amount of fence that we have. And it says that that perimeter right there is going to equal 76. All right. Okay, so we're almost there. Now, what we need to do is choose a variable that we want to replace, basically. Like, because we have 2 variables here and we need to get one in terms of the other, right? So what I'm thinking is I like to work with x's, right? And so let's get y by itself in this equation right here, because if we could get y all by itself, then we'll have a function involving x, and we could replace the y up here and turn our 2-variable problem into a 1-variable problem. So let's do that. Getting y by itself, I'm going to subtract 2x from both sides. Now, if I divide everybody through by 2, I end up with y equals x right there. And then half of 76 should be 35 plus 3, which should be 38. So let's try it. I think that 38 times 2 is 76. 2 times 8 is 16. 3 times 2 is 6 plus 1 is 76. Yes, okay, so I did that right. There we go. All right, so we're almost there. Next step, we're going to turn our 2-variable function into a 1-variable function. So now we have a, the area, as a function of x is equal to x times, instead of writing y, I'm going to write 38 minus x. Right there. Next step is graph it. I left it like this because it makes it super easy to graph. I could use my brain and figure out that the x squared term is going to be negative, so it's going to be a downward facing or downward opening cup. Also, x's are my inputs, area is my output. When I plug in a 0, I get out a 0. Plug in a 38, I get out a 0. And so this cup has to come up, come back down, and halfway between 38 and 0 has to be the max, because this is a parabola. Let's just see what's half of 30 would be 15 plus 3. So 18, I think. Should be that 18 is the x value, which makes the a value a maximum. Right there. Another way we could have done this is to say, and this is, even though I'm basically done, I could, what I want to do is make sure, I'd like to check myself. So what I'm going to do is rewrite this as 38x minus x squared, or in other words, minus x squared plus 38x, like that. Now I could see that my a term, because right now we have a parabola written in the form ax squared plus bx plus c. The a is -1. The b is positive 38. The c is 0. There is no c there. Which makes sense. And so now I know that my formula for the vertex, I know that the vertex of a parabola occurs at -b over 2a. And so I'm just going to plug in my values. negative b is negative 38 over 2 times a is negative 1. That's the same thing as negative and negative is a positive. So that's the same thing as just 38 over 2, which should be 18. Oh, you see? You see? I messed that up. Good thing I checked myself. 38 divided by 2 should be 16. Let's check. Here we go. 38 divided by 2. It goes in once, leaving me 1 left over 8. 19. I can't even get that right. So 19. Yeah, I'm just thinking the opposite way, right? So 19. Let's double check that. So 19 times 2 should be 18. 2 and 3 makes 38. Yes. Okay. So you thought you got me, but you didn't. Math. Okay. So all right. If I had done this right, I would have said halfway between 38 and 0 is 19. And here we go. So 38 divided by 2 is 19. In any case, we see that the vertex occurs here at 19. In other words, that's the input value to this function, excuse me, which gives you the maximum value right there. A bunch of ways we could approach this now. Now, since it says to find the max dimensions, let's just go ahead and find those, and then we'll check it by just multiplying it out, right? It says that x needs to be 19, okay? Right? Well, we have a formula for y. It's 38 minus 19, and that should be 19, right? It should be. Let's double check. 19 plus 19 is 8 and a 1 and a 38. Yep, there you go. So 38 minus 19 is equal to 19 right there. And funny, we would get 19 times 19 is my area. Okay, so let's look at that. And since it asked for it, we gotta state it explicitly. It says find max area. So that's 19 times 19. Can you see that? Yeah, the glare is not that bad. 9 and 9 is 81. 9 and 1 is 9, plus 8 is, I guess, 17. 1, 9, and that makes 6. 1 should be 361 right there. Area should be 361. I don't trust myself after what I just did. Let me double check that by plugging it in. I'm going to go 19 times 19. 361. Sweet. Okay, so the area should be 361. Also, look at this. What does that say to do? Basically, this, I could have plugged it into my area function, which is why I constructed it in the first place, right? It is the base times the height. We just rewrote it in a funky way, which gave me the base times the height, right? 38 minus 19 is 19, so you'd have 19 times 19. Or if we hadn't done it that way, if we had kept it as a of x equals negative x squared plus 38x, let's plug that in. Let's plug in 19 for x and make sure that we do get out a 361 like it says we should. So negative 19 squared plus 38 times 19. I guarantee you it's going to come out right, but let's just double check it. So we have negative 19 squared plus 38 times 19, 361. Okay, so no matter how you want to do it from there, you're going to end up with 361. So finally, what dimensions maximize the area? Well, 19 and 19. So in other words, a perfect square maximizes the area when there's no other constraints. when you're, which is to say, when you're only constrained by the perimeter, you're not constrained by a river or being up against a wall or something like that. A perfect square is how you maximize the area. And the max area is what you get when you plug in 19 into there, or equivalently, when you go through and you figure out what the base times the height is, 361. Chapter 9, section 6, problem 14. What is the maximum product of two numbers whose sum is 22? And what numbers yield this product? This is not conducive really to drawing, right? Usually we draw out the problem. That's what I said was step one with optimization problems. We could, if we wanted to, we could treat this as like an area or something like that, but this seems pretty straightforward, and I think we could skip the first step of drawing it out. We're going to say, okay, the maximum product of two numbers. So then the thing we're trying to maximize, the thing that we're trying to optimize is the product itself, right? So what is a product? A product is when you take two numbers and multiply them together. What do you want to call the two numbers? How about x and y? Okay, so we're trying to do this. That is the quantity we want to maximize, is P. That's what we're going to call it. P is the product. Okay, whose sum is 22? All right, well, then that's my constraint, right? So I'm starting with a function of two variables. I want to drop it down to a function of one variable, and I need a constraint to do that. And we are constrained by their sum of these two numbers is 22. So, okay, let's just write that out. 22 equals the sum of these numbers, x plus y. Okay, now we could solve for either one of these numbers. It's going to be exactly symmetric either way we choose to do it. So I'm going to say, let's get y by itself. So we'll subtract x from both sides. We'll have 22 minus x equals y. Now I'm going to say, okay, well, let's just substitute in for y, my original equation. P is equal to x times y, but now y is 22 minus x. Cool. This is a function. It gives an input, right? We have one input. It gives me an output. I'm going to think about this as a function of one variable, p of x. Now let's graph this guy. It's a parabola. I could also see that this is going to be 22x minus x squared, or minus x squared plus 22x. This should be a downward opening parabola, right? And I could see that when I plug in a 0, I get out a 0. When I plug in a 22, I get out a 0. And so it's got to do something like this. Halfway between is where it's going to go through. So we should go through right there at 11. Okay. Another way I could do that. Remember what I'm doing here is I'm thinking different x inputs, thinking about different y outputs, or p outputs, values of the product. And another way I could find that is saying, well, hold up, that's the vertex. That's the vertex of a parabola. The a value here, because we have this in the form of ax squared plus bx plus c, the a is -1, the b is 22, and I could say, oh, and this, of course, the c is 0. I could say, well, the x value of the vertex occurs at -b over 2a. So we have -22 over 2 times a is -1. A negative over a negative is a positive, so we're left with 22 over 2, which is 11. So yeah, that works both ways. Okay, so we're part of the way there, right? What numbers yield this product? Well, one of them is 11, right? Because we found x, the x that maximizes the output value here. Output being the thing that we're trying to maximize, the product. When the input is 11, the output is a maximum. And we could go ahead and see, like, well, we should plug it in and see what it is. When I plug it in, I plug in 11, I get, I'm just going to use this formula right here. 11, 22 minus 11. It's just 11 times 11. Uh-oh, it's 11 times 11. It should be 121, I think. Right, 11 times 10 would be 110 plus 11 should be 121. Yeah, okay, there you go. So that output, the max output that this function can give me, the max that the product could be is 121. And indeed, yeah, that's kind of what I did, right? And even plugging it back into this is nice because I could see that, yeah, that's how you got the y in the first place, right? 22 minus that max x is 22 minus 11 is 11. And so y equals 22 minus 11 at its max. So that y equals 11 at its max. And what do you know? If we had set this up like an area, right? Like what is the max this way, or what values this way and this way, and so on and so forth, we would have also found that we end up with a square. What x and y is, just like with the last problem. We're constrained by some amount of stuff. In this case, it doesn't go all the way around. We're just constrained by this half of the perimeter right there. But it still turned out to be that the overall shape, which maximizes the area, which if you think about this in terms of area, it's symmetric, right? It's still a perfect square that does it. So finally, what is the maximum product? The max product is 121. What numbers yield this product? 11 and 11. Chapter 9, section 6, problem 16 says, what is the minimum product of two numbers whose difference is 4? And what are the numbers? It's very similar to the one we just did. And so, again, this does not lend itself to a picture. So I'm just going to go ahead and say, okay, what's the thing I want to optimize? What's the product? Product is the thing I want to find the minimum of. The product of what? Well, two numbers. What are their names? How about x and y? Okay, so that's what I'm trying to do. Now, what constraint do I have? Well, it says that the difference of these numbers is 4. So how do we write that? The difference of two numbers would be x minus y. Doesn't matter what order we use. We'll see that in a minute. And it says that difference is 4. Okay, so let's see. We want to take our 2 variable function and drop it down to 1 variable. Let's get the y by itself. I could add y to both sides. This would be 4 plus y equals x. And then I could subtract 4 like that, x minus 4. We could have done it with we could have got x by itself easier. That would have been all right too. But that works. So let's go ahead and do it. We're going to plug that in to get a new function of 1 variable now, x times y. Only y is now x minus 4. I could see that this is an upwards facing parabola, right? Because that x squared term is positive. So that means it's going to be an upward facing cup. I could also see by looking at it this way, that this thing is going to go through here at 0. And it's going to go through here at 4. And so 2, and let's kind of finish this picture here, right? It's an upward facing cup. So that means it comes down like this, dips up, boom. And halfway between it is where we have our min, which is going to be here at 2. Alternatively, we could have said, well, the vertex of this guy occurs at negative b over 2a. Negative b here is negative 4. Negative 4. 2 times a here is positive 1. So we have a negative 4, which is positive 4. 2 times 1 is 2, and we have a, lo and behold, we have a 2, which is what we got that way as well. So finally, we're going to say, all right, we could plug this guy in here and see what we get out as the product. And let's see what happens when we do that. I'm expecting a negative number, actually, because I could see by the shape of this, I should end up with something negative. Plug in a 2 for p into p. Plug in a 2 for x, and we get 2 times 2 minus 4 right there, which is 2 times negative 2, which is negative 4. My output should be minus 4. We could have figured that out by plugging it into here as well, right? 2 squared minus 4 times 2 would be 4 minus 8 is minus 4. Either way you want to do it, you end up at the same place. Or we could have done it this way. We could have said, well, we know the value of x, which minimizes this product, right? We get the lowest value out right there. We also know that y is equal to x minus 4. So when x is equal to 2, it's minus 4. So that y equals minus 2. This was the other part of the problem we needed to find anyway, right? So what is the minimum product? Well, that's the minimum output right there. The minimum product is equal to minus 4. What are the numbers that gives that to you? There is numbers are 2 and minus 2. And we could just double check that their difference is indeed 4. If you take 2 and subtract negative 2, you do, get a 4. We're not going to go through it, but if you had chosen to do it the other way, it would have worked out. We saw that in the very first one of these that we did with the quizzes, right? If you switch the stuff, right, that yeah, it's going to look a little bit different. You probably would have ended up getting, instead of 2, you would have got negative 2, and then so on and so forth. But in the end, you're still going to end up with 2 and negative 2 as the two numbers that do it. And the product is still going to be negative 4. Chapter 9, section 6, problem 26. An orange grower has an average yield of 40 bushels per tree when they plant 20 trees per acre. Adding 1 tree per acre decreases the yield by 1 bushel. Okay, so think about it. You try to cram too many trees into a small area. There's crowding and congestion, and every time you try to cram 1 more tree in, you decrease your yield by 1 bushel. How many trees per acre should we plant in order to maximize the yield? Now, a picture on this to draw is going to be interesting because, well, okay, kind of talking about rates here, right? Like it doesn't say that we have a 20 by 30, plot of land or something like that. And so, man, what do we do in this case? Well, what I'm going to do for right now is forego the initial picture. We will be drawing a picture, but it's not going to be quite a representative of like a farm or something like that. But right now, so let's skip step 1 and go right to how many trees per acre to maximize the yield. So we want to identify the quantity that we want to maximize, and that is yield. We want to maximize the yield. Okay, so let's write a function which gives us the yield. What do we know about the yield? It says that we get 40 bushels per tree. Now look at this though. How many trees per acre to maximize the yield? So what we want is our output of the function that we want to maximize to be the yield, right? We want, and let's call it y for yield. And what we want is the input to this function to be trees per acre. If we imagine what's going on, right? Trees per acre, and then who knows, maybe we have some other stuff over here. Maybe we're multiplying by a bunch of stuff. Who knows? But ultimately, what we hope we end up with is something like this, right? Where the input is trees per acre. And the output here is our yield. Okay, so that's what we're aiming for. How can we do that? Well, let's think about this, because when we have, so it says that we have an average yield of 40 bushels per tree. So it looks by yield, what we want is bushels, right? We want as many bushels as possible. And it says we have 40 bushels per tree when we have 20 trees per acre. And then for every one tree that we add per acre, it decreases by 1. And what I'm seeing in my head is a picture. This is where it gets tough, right? That the picture we're drawing isn't a farm, it isn't a square, it isn't a picture frame. But the drawing that I'm thinking about is this. It's a relationship. That something is decreasing every time we increase something else. In other words, when I increase something, some value that I care about is decreasing. What's the value? Well, it says adding 1 tree decreases the yield by 1 bushel. So we could think about bushels per tree, right? It says an average yield of bushels per tree when 20 trees per acre are planted. So let's think about this. This is saying is that I think of my input as 20 trees per acre. When I plug in 20 trees per acre, my yield, my output, it says is 40 bushels per tree. Bushels per tree. I'll just go B or T like that. And it says every time I add 1 tree per acre, right? So when I'm at 21, I've decreased down to 39. And so on and so forth, right? What about at 22? I go down. What's nice is that these are all in a nice line, right? It says every time you add 1, you go down by 1. So it's actually really nice. We could work with this, right? So what's nice already, I could see there's a lot of different ways I could do this. But what's going to help me, in this case, our picture that we want to draw is actually a function. So let's draw it out. What is this? Well, it's a line that has a slope, and I can tell the slope is -1, but we'll get there. It's going to look like this. All right. Okay, so what's the formula for that line? Well, let's think about this. Let's give some names here. The trees per acre, I'm going to call T. Okay, so that's going to be trees per acre will be represented as T. Bushels per tree is going to be B. We'll just call it B, bushels per tree. This is bushels per tree. That's what's going on. Okay, so when I'm planting 20 trees per acre, I get out 40 bushels per tree, right? So what I want is B, my output thing. I can see it's a line, right? And every line has a form mx plus b, but in this case, I'm calling it T for trees per acre. So m T plus little b right there. I already know what the slope is. I already said it was a -1. We could check that if we want by saying, well, hold up, what's my slope? My rise over my run here. Well, when I run 1 unit right here, right, I'm going from 20 to 21. 1 minus 20 is 1. Well, yeah, you just look at the picture. That's 1 unit right there. I go down by, well, what was 40? Down to 39, or rather 39 minus 40 is -1. It's not really how I think about it. I just think about it as a distance. The distance from 39 to 40 is 1. And it's a fall, so it has to be -1. So the rise over the run, it's actually a fall over a run, -1 over 1 is just -1. Okay, so I'm halfway home, right? I could say, so this thing that I'm trying to figure out, the bushels per tree is equal to -1, I'm just plugging that in for n, times trees per acre plus b. The only thing I don't know is that y-intercept right there. Cool thing is, I do know that when I plug in a 20, I get out 40. Okay, so in other words, when trees per acre is equal to 20, my output in bushels per tree is equal to 40. So I'm going to go ahead and plug that guy in. In fact, I'm going to clean this up a little bit first. I'm going to say the function I'm working with is -t plus. Now, what did I just say? When the input is 20, so minus 20, let's see, the output is 40. I think output 40. Okay, so that's 40 equals minus 20 plus b. Add 20 to both sides, and I get 60 is equal to b. Now that's what I was looking for. And this actually makes sense, right? I mean, like if you go back 20 units and you've gone up for every one, then you should go up 20 units up to from 40 up to 60. So that looks good. So I'm going to rewrite this. My bushels equals slope times trees per acre plus b is equal to, this, the m is a -1, so that's just a minus t, and the b was a plus 60. All right. So, okay, now we have a picture, but how's this going to help us out? Okay, what is it asking us to do? How many trees per acre? Okay, so input trees per acre. That's what we're looking for. That's what we want. Our input is trees per acre. And we want to maximize yield. Well, let's think about this. What is my yield? So yield. It's, I guess, if we know how many, how many trees per bushel, wait a minute, how many bushels per tree we're producing, and we multiply that by the number of trees we have, right? So let's think about this. Trees per acre is my input. My output is bushels per tree times number of trees. I should get my total number of bushels. That is my yield right there. Does that make sense? Let's think about this. Hold on. Now, everything we're dealing with, we have bushels per tree. Yep, something like that. Many acres. I think this is the only way to get a yield out of this, right? Bushels per tree times the number of trees should give me the total number of bushels that I have. So we have a function which gives us bushels per tree, right? And it's saying how many trees per acre. And so actually, I don't know how many actual trees I have, right? But I can say, because that's not what we're messing with, right? We want trees per acre as my input. That's going to be my input right there. So then we would know, well, I guess how many bushels per acre would be my maximum yield. And so does this make sense here? Where we want to know how many trees per acre maximize the yield. So my input is trees per acre, which I have called T. And so we take T and then we multiply it by the number of bushels per tree, and we'll have bushels per tree times trees per acre should give me bushels per acre, which is the yield. They didn't explicitly say this. If they had just said how many bushels per acre should we get, or how many trees per acre should you plant to maximize bushels per acre, then this would have been a no-brainer, right? We had, and I have to, you heard me say it over and over again 5 times. I have to say it over and over again to convince myself that this is what we want. So given the way the problem is worded, this is the quantity I believe that they want us to maximize. Okay, bushels per acre. And in the context of the problem, that's it. They never ask how many trees should you plant to do it. No, it says how many trees per acre should you plant. And so we can't tell how many bushels there are because we don't know how many acres there are. So it makes sense that our yield should be in terms of bushels per acre. Yep, and there you go, right? Average yield of bushels per tree. Yeah, and so yeah, it's still kind of up in the air, but this is the only thing they can mean by this. To maximize our yield, they must mean our overall yield. So I feel pretty confident about this. This is the quantity we want to maximize. Okay, we have a function. We have a picture, but whoa, that's a different kind of picture than what we were expecting, right? But that's okay. That's okay. This is the picture that we used in order to find in this case, it's not really a constraint. I mean, we kind of are, this really, technically, this is our constraint. We're constrained by how many trees per acre we do. The more trees per acre we have, the less our bushels per tree is going to be. And so that is our constraint. We're going to use this to take, and again, this is kind of in a sense, it's a 2 variable problem, right? Because you have bushels per tree and you have trees per acre. And what we've just done is we've written bushels per tree in terms of trees per acre. And so we've reduced this down into a 1 variable problem. Whereas before, I remember what I just did here. I said bushels per tree. I called that over here, I called that big B. And then I called trees per acre over here, I called it little t. And so we're saying y is then equal to b times t. And the problem is, well, that's a 2 variable function. We need to drop it down into 1 variable. Well, that's what that does. We could get b in terms of t. And so we could say that y is equal to big B is now minus t plus 60 times t, which I could write this a few different ways. I would actually like to first write it like this: 60 minus t times t. What would you write now? Because now we have trees per acre. And I have that written right there. T is equal to trees per acre is my input, and my output is bushels per acre. But let's look at this. This is a downward facing parabola, right? Because this is the same thing as negative t squared plus 60t. I actually did that by doing this one up here. I wrote that here for what you're going to see in a second. Graph this guy. And it is what we expected at the very beginning, right? It should be a downward facing parabola. We're going to try to find the max of something. So downward facing parabola, it goes through at t equals 0. And it goes through at t equals 60. Downward facing means it comes up and goes back down like that. Halfway between where the max is, which should be at 30 right there. That's what that means. Now we could do it the other way where we say, well, A, right, this is AT squared plus BT plus C. A is -1, B is positive 60, C is equal to 0. And so my vertex, I'm not going to call it X, we are doing T. The T value of the vertex is going to be at -B over 2A. Negative B is negative 60 over 2 times -1. Negative is a positive. So we have 60 over 2, which is 30. However you want to do it, you're going to end up with the T value of your vertex is equal to 30. And we could say, okay, then what is my output? Well, that would be y of 30. y of 30. We could do it this way. It looks kind of hard. I'd rather do it this way. Let's say y of 30 is equal to 60 minus 30 times 30. 60 minus 30 is 30. So that's 30 times 30, which is 900. 30 is equal to 900 right there. Okay. They didn't ask for that. They didn't ask what was the max yield, but I like figuring that out for myself. I could see that the height of that parabola is 900, or that my maximum yield will be 900 bushels per acre. That is the way I can maximize it. And how many trees per acre to maximize that yield? Well, what was T? T was trees per acre. So the value of T that maximizes the output is 30, which means finally we get our answer. We could say 30. When T is equal to 30, that means we have 30 trees per acre will maximize the yield. There's another way to attempt this problem. You could say my yield would be, well, the bushels per tree times trees per acre, right? And that's what we did, the bushels per tree times trees per acre. You could say, well, you know that when you have 40 and 20, right, you just have 40 and 20, and for every one that goes, for every extra tree that you plant, you go down by one here and you go up by one here. So you could say something like this. Bushels per tree, you're starting at 40. And trees per acre, you're starting at 20. And then for every one extra tree you plant, this goes down. So how about minus, let's go let T equal number of extra trees you plant above 20. So you say, okay, so then for every extra one I plant above 20, this goes down by 1. So you could say minus 1 off for every extra tree. And then, well, of course, then this would be plus T right there, because for every one extra tree you have above 20, you have a total of 20 plus T right there. And now we have a function which, let's just kind of see what happens. It has a 0 here at 40 and a 0 at minus 20. So that's the function we want to optimize. It should look something like this. Plug in a 40 and we get out a 0. Plug in a minus 20. Oops. Excuse me, we get a 0. And when you multiply this out, first, outer, inner, last, you get 40 times 20 is, well, let's do that real quick. 40 times 20, 0, 0, 0, 8. I should have been able to do that. 800. Outer gives you plus 40, inner gives you minus 20, so a plus 20t. Finally, negative and positive gives you minus t squared. So we can say that y of t is minus t squared plus 20t plus 800. And say, okay, it's a downward facing parabola. So it goes down like this. Halfway between there is like 10. And you'd say, let's double check that the t value of the vertex should be minus b over 2a. So it should be minus 20 over 2 times -1. A minus minus is a positive, so you have 22. There you go. That's the t value of your vertex right there. And you would find that if you plug that in, you would maximize your stuff. The max value, y of 10, let's say, okay, y of 10, it's the same thing as 40 minus 10 times 20 plus 10, which is 30 times 30. And hey, that's what we got before, right? That was 900. And so, yeah, the max value that you get is 900. And you're right. And then you would say, well, then the number of trees that you need is 10. Yes. Number of t is the number of extra trees you plant above 20. So you have to be very careful with that. You don't want to get in the habit of going, oh yeah, the vertex is the value and blah, blah, blah. What you've done here is something very different, right? You've said, well, wait a second, hold up, we could go above and go below, but there's a specific number that t means. It's the number of extra trees you plant above 20, right? Because when t is 0, that means that you have 20 trees per acre. When t is 1, right, then you have 21. Remember, this value right here is the number of trees per acre. And so with t being 10, that's the number of extra trees that maximizes your value, right? That maximizes the yield. And so the total number of trees is what you get when you plug this guy in right here. And you get that the actual trees you want, the number of trees to maximize yield is 20 plus t, that value right there, 20 plus t trees per acre. And so 20 plus the TV that we found, right? 20 plus TV would be 20 plus 10, which is 30. Right there. So either way you do it, you should end up with 30. You should not end up with 10. And so, yeah, you got to be very careful when you try to do a slick relation like that. That's why I love to have my variables written down right here. Because then at the very end, I go, oh, TV equals that. Wait a second, well, what is T? And just like I did when I did the long way, right? I said, wait a minute, T was equal to trees per bushel or whatever it was, trees per acre, which was the thing that we were looking for. In this case, T was not equal to trees per acre. It was the number of extra trees above 20. And so with 10 extra trees per acre above 20, then we have a total of 30 trees per acre. Chapter 9, section 6, number 28. Find the dimensions of the largest rectangle that can be inscribed in a right triangle as shown. By inscribed, they mean that this rectangle here touches the hypotenuse at one point like this. Maybe it's really long and skinny like that. Or maybe it's long and skinny this way, right? But that's what they mean by inscribed, that it touches here. That corner touches at one point. Okay, they've already given us a picture. And they've also went ahead and told us this thing right here. That one is 15 long. This is 9 and this is 12. There's a hint that 15 is only going to screw you up. It is not going to help us out at all. And so I'm going to go ahead and forget about it. I didn't even draw it initially and write it down. Okay, so step number 1, draw a picture. Are we done? We've drawn a picture. Yeah, but here's the thing about this is this picture isn't really going to help us that much. It's going to be much, much better if we go ahead and put this on a Cartesian coordinates. And this is going to be the case with a lot of things. they give you a situation like this, it's probably best to just go ahead at the very beginning and frame it in terms of Cartesian coordinates. And since we have a nice right angle right here, it's a right triangle, so we know that means a right angle. Let's go ahead and just extend this up this way and extend this out this way. And since that side has length 9, we know it goes through here at 9. If that side is length 12, we know it goes through here at the point 12. Now we could say, well, this thing, this triangle or this hypotenuse or whatever, it's just a line. And this line, every line has the form y equals mx plus b. Okay, that's going to help us out. Now, we're not done because what are we trying to find? Well, we know we're going to find area. That's what they want us to do, to find the dimension of the largest rectangle. They mean to maximize the area of this guy. And so in order to do that, we're going to need a base and a height. And so how do we want to do that? Well, I guess let's just go ahead and call this, call that length right there x. We'll call this length right here y. We're almost there. The largest rectangle, they mean to maximize the area. So let's go ahead and do that. The area is equal to x times y right there. Now here's a hint. We're on Cartesian coordinates, right? So instead of thinking about this thing as a length, we could think about this as an x input value right here. We're somewhere on the x-axis. Where is x? Well, it's somewhere between 0 and 12, but that's the idea. Ditto here for y. Y, that distance right there, we can think about that as an output value, a y value like that. Now, okay, we've identified the quantity we want to maximize, that's A. We have a function which gives us A, area, as an output. The problem is we have two variables. We don't know how to deal with two variables. So we're going to say, all right, if we could somehow change one of the variables into the other, oh, we have a line right here. If we could get the equation of this line, because look at this, like this is very suggestive here. It doesn't matter what x value I plug in. Just like earlier, I said, what if x were right here? Well, it would go up to there. We're constrained by the height of this thing. But what is the height of that thing? Well, that's the output value of this line, of that function, right? If we're over here, all the way over here, we'd be constrained by this, but this function tells us how high up to go. So in other words, what I'm saying here is that if we could find the equation of this line, then this value y, the height right here, will be mx plus b. The only thing that remains is to find the equation of this line. Well, let's look at this. We have two things we need to find, m and b. And we could find the slope pretty easily because we know the slope is the rise or the run. And so the rise in this case is a total of 9. It's not a rise, it's a fall, right? We're going down, so it's a negative 9. The run of this line is 12. And so negative 9 12, so I guess that's the same as negative 3 times 3 over 3 times 4, the 3's cancel, m is negative 3/4. Okay, so we're halfway there. Y is equal to negative 3/4 x plus b. We also know that when we plug in a 0, we get out a 9. And so I plug in a 0 here for x. I get out a 9. You could also say, well, the y-intercept is 9. Yeah, that's what all of this means. The 0 goes away, and we're just left with b. And so that m was equal to minus 3/4. B was equal to 9. And so the function that we're looking for tells us that we have, I'm just going to go ahead and replace it right there. Mx plus b is minus 3/4 x plus 9. We also could have done this by plugging in a 12 and getting out a 0. Just want to show you what I mean by that. Right? We're trying to find b. We could have plugged in a 12 and got out a 0, in which case we have 0 equals negative 3 times 12 over 4 plus b. 0 equals 12 divided by 4 is 3. So we have a minus 3 times 3 plus b, which is negative 9 plus b is 0, or 9 equals b. Either way we do it, you can use any point you want on a line, and you can use it that way. At any rate, we have that b equals 9, and that n equals negative 3/4. And so what we have finally is a way of relating x in terms of y, or y, I'm sorry, in terms of x. And so we have that the height y is equal to minus 3/4 x plus 9 right there. So you give me any height or any length of that guy, any base, and I can tell you how high up it has to go. You give me, say, a 4. If I plug in a 4, this thing says you go minus 3/4 times 4 plus 9, and we get the 4's cancel, minus 3 plus 9. Minus 3 plus 9 is 6. And so I know that my height here would have to be 6. And so my area would be 6 times 4, and so on and so forth, right? But we could do this all in one step by just saying, well, let's replace that. And of course, that was the whole goal, is to turn my output function into a function of one variable. And so instead of x times y, I'm going to say x times minus 3/4 x plus 9, which I could rewrite as, but before we do that, let's go ahead and just graph it. You can tell it's going to be a downward facing parabola because we're going to have a negative 3/4 x squared plus 9 times x. And so it's a downward facing parabola. It's got to go through here at 0. And again at, let's see, minus 3/4 x plus 9 equals 0 whenever 9 is equal to 3/4 x, which happens when x is equal to 9 times 4/3. The 3's cancel, we get 3 times 4 equals x, or how about 12 equals x? So it has to go through up here at x equals 12. It's a downward facing parabola because of the negative 3/4. And so 6 should be halfway between. That should be the value that maximizes this. Let's just make sure here. We're going to use our vertex formula. We're going to say that the vertex occurs at negative b over 2a. And so, okay, b, this is ax squared plus bx plus c. A is equal to negative 3/4. B is equal to positive 9. C is equal to 0. And so negative b is negative 9. 2 times a is minus 3/4. Oh, that looks familiar. Huh, that's exactly what I did there. So a negative and a negative is gone, and we have 9 over 2. 3/4, that's the same as multiply by 4/3. So I'm going to put my 4 up here and my 3 down here. Right? Multiplying by the reciprocal, getting rid of the negatives. The 3 cancels here with the 3. 2 cancels here with a 2, and I should end up with 3 times 2 is 6. So, yep, the x value of the vertex is 6. So the input value happens here at 6. So when x is equal to 6, and what we could do is then just plug it in and see what we would get, right? Say the y output value occurs when the input value is 6. Okay. So let's see, negative 3/4 times 6 is 2 times 3. So I guess we have a 2 that cancels down here. 3 and a 2, so that's negative 9/2 plus 9. negative 9 halves plus 18 halves is 9 halves. So the y value should be 9 halves. I'll go ahead and write it right there. Says what dimensions? Find the dimensions of the largest rectangle. Well, the dimensions would be 6 and 9 halves. The area itself would be 6 times 9 halves, which we can obtain by doing multiplying them together, right? Which gives us 9 halves times 6, which would be 9 times 3, which is 18. Or I could plug it right back into here or into here and see. I just want to double check that that actually works, make me feel good about all of this, that the output value should be 18. So let's see what happens when I do plug in. So I plug in 6 and let's see what comes out. 6 times minus 3/4 times 6 plus 9. We get 6 times, yeah, this is looking very familiar. 3 times 6 is 18 divided by 4. That is 9 halves. Yep. Negative 9 halves plus 9. I'm going to write 9 in terms of halves, so that's 18. Indeed, we are getting 6 times positive 9 halves, which is 2, gives me a 3 and a 9. 3 times 9 is 18. Okay, so that works too. 18 is the largest output we could get for area. And so the dimensions of the largest rectangle that can be inscribed are 6 down here and 9 halves right here. Chapter 9, section 8, problem number 6 says that a business earns $1,000 in the first month, $2,000 in the second month, $8,000 in the third month. We are supposed to fit a quadratic function to the data. Use that to predict the earnings for the fourth month. And I have added on to that. Determine if that function that you find has a min or a max. If so, where does it occur and what is the value? Here I'm saying, where does the extremum occur and what is the extreme value? Just a fancy way of saying either min or max. Okay, so let's look at this. We're supposed to fit a quadratic function to the data. So what we want is an f of x. It's supposed to be quadratic, so it has to be ax squared plus bx plus c. And it tells us that when we plug in, I guess we're just going to say let x be the month, right? So when we plug in a 1, we get out 1,000. Plug in a 2, we get out 2,000. Plug in a 3, we get out 8,000. So let's do that. We get out 1,000 when we plug in a 1. And so that's a times 1 squared plus b times 1 plus c. We get out a 2,000 when we plug in a 2. B times 2 plus c. Finally, we get out an 8,000 when we plug in a 3. So making this a little bit nicer, we could say this is the same thing as a plus b plus c equals 1,000. This says 4a plus 2b plus c is equal to 2,000. This says 9a plus 3b plus c equals 8,000. Right? So I didn't do this explicitly. What I've done here is written f of 1. This is f of 2, and this is f of 3. And that gave me this nice system of equations. 3 equations, 3 unknowns. We could solve this. The easiest way to go forward is to use a matrix. And so, at least I think rather the most straightforward way is with a matrix. This is a way that you can guarantee you're not going to fail. Well, yeah, anyway, so everything's lined up in nice columns. My first column will be my A's. My second column will be B's. My third column will be C's. And my fourth, my augmented column, will be these output values right there. And so let's go ahead and write that down in matrix form. It's going to be 1, 1, 1, 1,000, 1, 1, 1, 1,000, 4, 2, 1, 2,000. Right, 4, 2, 1, 2,000, and then 9 A's, 3 B's, 1 C, so 9, 3, 1, 8,000. All right. So we're going to do this the way that we've done it in class. We're going to say, all right, I need to kill that guy and that guy. I can kill that guy by multiplying the top by -4 and adding it to the middle part, giving so I'm not touching the top one. Adding that to the middle one gives me a 0, -2, -4, and that is -3. -4 and 2,000 is -2,000. Okay, I'm going to do the same thing for the bottom row. To kill the bottom row, we need a -9 right there. So -9 times the top row gives me that, -9,000. -9 and 9 is 0. That gives me a -6, a -8, and a -1,000. Okay, nice. Now let's get leading ones. We're going to get leading ones right here. So dividing everybody through by -2 right here will give me a 1 right here. And I don't think this glare is going to be too bad. I know there's a glare right here. It shouldn't be too bad. So dividing this thing through by -2 gives me a 1. How about +3/2? And then by a -2 gives me a +1,000. That's nice. Dividing this thing through by -6 gives me a 0. Can you see? Oh yeah, you can see that. 1. Now -8 over -6 is the same as +4 over 3. Yeah, 2 and 2. Yeah. Okay, so +4/3. Now, -1,000 over -6. That's the same as +1,000 over 6. Or how about +500 over 3? That should do it. Multiply the top by 2. Bottom by 2. Yeah, okay, we're good. So 500/3. Okay, now let's see. I'm going to use this one to kill that one. And I'm not touching the top row yet. 1, 1, 1, 1,000. This row is not going anywhere. 1, 3/2, and 1,000. Now I'm going to multiply this, or no, I'm sorry, I'm just going to subtract. That would be the easiest way. I'm going to take this -1 gives me 0. This minus that is 4/3 minus 3/2. That's the same thing as multiply top and bottom by 2, 8, 6. Multiply the top and the bottom by 3. That gives me 9/6, which is -1/6. So that goes right here, -1/6. Uh-oh. I said I was going to take this and subtract that. So that's 500/3 minus 1,000. 500/3 minus 1,000 is the same as 3,000/3. So that's minus 2,500/3. I believe. Yep, minus 2,500/3. But we make this a lot easier by multiplying that thing through by -6. So if I multiply that entire row through by -6, that turns that into a +1. The negative makes that a positive. The 6 kills that, and we have 2,500 times 3 leaves me with 2. So 2 times 2,500 should be what, 5,000? Yeah, let's make sure. 0, 0. 2 and a 10 and a 4 and a 5. Yes, 5,000. Okay, so multiplying that through gives me a 5,000. Okay. All right. This ain't bad. We're almost done. So that needs to be a -3/2. So if I multiply this by -3/2, multiply that by -3/2. Let's just do it. 5,000 times -3/2. That's the same thing as -3. 2 just did that. It's 25. And then 25 and a 3 gives me 0, 0, 15, 6, and a 7. So 7, 5, 0, 0. Oh, buddy. I'm so sorry. Oh, Kayla's not here, buddy. We're just doing a video. Yeah, I'm sorry, bud. It's okay. It's okay. And so I'm going to add that to there. The bottom row is not changing. That is what I want. We have a 5,000 right there. Add that to that. 0, 1. Yeah, crackers, buddy. Uh-oh. 1,000 minus 75 should be minus 650 right there. Yep, that looks good. Okay. Now let's do the top. Oh, the top one's nice and easy. So we could just say, take this and subtract that. That minus that is 0. That minus, or rather, that minus that is -4. There we go. Okay, last thing to do. We're going to take, I got to get rid of that guy. So I'm going to say, just take him and subtract him off. Bottom thing is not changing. The middle finger is not changing. Now, we take that and subtract him. One stays put, we go there. That and that is gone. That subtract by that is 65 minus 4 should be 25. Just make sure. 5, 2, 4, 5, 6 is yes, 25. Okay. So 0 and 2, 5, 0. Okay, that should do it. This means that A plus 0, B plus 0, say blah, 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 is equal to 2,500. B is equal to -6,500, and C is equal to +5,000. So finally, I didn't have it up here because I got rid of it. We said that our original function that we were using to model the data, ax squared plus bx plus c, we found that a is equal to 25x squared. The b is a minus 6, 5 double z x, double 0x, plus c is plus 5,000. There we go. That is a quadratic function to fit the data. That is what we wanted. Okay. Now, we could go ahead and take care of this stuff. Determine if the function has a min or a max. Well, this means it's an upward facing parabola, so it has a minimum value. Let's find what it is. Where does it occur? Well, we know that it occurs at its vertex, which is at -b/2a, which is -6,500 over 2 times 2,500. Which, okay, negative is a positive, so we have 6,500 over 2 times 2,500 is 5,000, okay? So actually, when we could do this, if you've ever seen this trick before, cross those zeros out. This is the same thing as 65 over 50. Oh man. So that the vertex value occurs at. Well, 65 is, it's 13 times 5, I believe. Oh, I didn't check that. 5 or 1, 6, yes, okay, so 13 times 5. 50 is 10 times 5. And so the x value of the vertex is 13 over 10 right there. Okay, so that is where it occurs. What that means is 13 over 10 is 1.3. That means that the minimum value occurs somewhere between the first and second month, because we're talking about in terms of months. 1.3 would be 1.3 months. So it would be between month 1 and month 3. It'd be 0.3 after, a third of the way after the first month. What is the extreme value? What is that minimum value? Well, we could just plug it in here and find out, right? So let's do that. 13 over 10. I'm going to plug it in and see. 13 over 10 is 25 double 0. 13 over 10 squared minus 6,500. 13 over 10 plus 5,000. I'm going to plug that into a calculator real quick and find the answer. You have a good nap, buddy? I get 775. So what is that extreme value? Well, going back to what we got here, it says that here at 13 over 10 or at 1.3, the minimum value that we got out was $775. In other words, that at 1.3 months, and this is just more of an exercise to get you into, to have some practice talking about extreme values, mins and maxes. I would say that according to this model, we could predict that our earnings at 1.3 months were 775, although it doesn't really work with the data. That's not really how finance works. But finally, we could say predict the earnings for the fourth month. Well, all that is what do we get when we plug in a 4 for the input value? Because we're talking about months here. And so the fourth month would mean that for X, we just plug in a 4. And let's see what that does. So we'll have f of 4, the earnings for the fourth month, will be what we get when we do this. Again, I'm going to plug that straight into a calculator. And so that's 2,500 times 4 squared minus that times 4. I get 19,000. And so for part B, predict the earnings for the fourth month. We can predict $19,000.